Hello friends, today we will continue our lecture series on solving previous year GATE questions. Today's we will start with the subject electronic devices and circuits. Here, as you can see on the screen, the question we have taken is from the module of semiconductor physics. That is the first module of the subject EDC. This question appeared in the year of GATE exam 2021 for 1 mark. So let us start solving the problem. So now before starting any problem, first we need to read the question very carefully and try to extract what is already given and what we have to find. Based on that, we will deduce a method to solve the question. So let us start and see what is exactly given in the problem and what exactly we need to find. Okay, so here a silicon is doped with a boron concentration of 10 power 16 per centimeter cube amount. Means we have 10 power 16 atoms which will be doped in per centimeter cube volume, and so this is our doping concentration. What you call that doping concentration? Either if your semiconductor is becoming N type, then you will call that doping concentration as Nd, and if your semiconductor is becoming NP type, then the doping concentration will be termed as Na. So now we can think and settle exactly what happened in this question. So now, as we all know, boron is a pentavalent impurity. So we all know that boron is a trivalent impurity. So whenever a silicon bar or a semiconductor intrinsic bar is doped with a trivalent impurity, the resultant semiconductor will be our p-type semiconductor. So we can term here our concentration 10 power 16 is nothing but Na, which is equal to 10 power 16 per centimeter cube. Now, and we here he has given that the full ionization has taken place. That means the amount of boron which we have given will be completely entered into the silicon bar, and all the atoms has taken the specific location, so there will be no loss. So we have to consider complete 10 power 16 atoms. Next, what next is given is the generation rate. The generation rate of electron and hole pairs, which is of the value 10 power 20 per centimeter cube second. Means what is generation rate? Generation rate is, we can term it as, if some outside energy is given, then what is the rate at which electrons are coming out of the bond, that is in your valence band, and moving to conduction band, and what remains in the valence band is your hole. So what is the rate at which this whole electron pairs are getting generated? So what is the energy source? This question is telling us the energy source is your light. We are exposing your semiconductor to light. Because of that light, these electrons and whole electrons in valence band are getting some energy. They are breaking the bonds and moving to conduction band, and a hole remains in the valence band. So that is the whole electron pairs are getting generated. At what rate? Means in a volume of 1 centimeter by 1 centimeter by 1 centimeter, you are getting 10 power 20 atoms per second. So that is the interpretation here. So now we will term this thing as G, which is equal to 10 power 20 per centimeter cube second. Fine. Let us move ahead. Now we have given the recombination lifetime, that is 100 microsecond. Then what is recombination lifetime? The recombination lifetime is a time span for which these electron hole pairs which is getting generated will remain, and after this lifetime that whole electron pair will get recombined. So what is the lifetime? Lifetime is your 100 microseconds. So it is given by tau, which is equal to 100 microseconds. So now remember one thing here. Most important is whatever units you are getting, you have to normalize all the units to a single unit. That means if we are getting in the question centimeter, meter or mm, let us consider these three units we are getting. So we have to normalize it to either of one. Every value will should have same unit with it. Means if you are having some value as centimeter, reduce other values of in meter or mm to centimeter and then solve the question. So now here we already have a second available with us. So we will normalize this microsecond to second, which will be 100 into 10 power minus 6 seconds. Okay, what is next? Next is given is intrinsic carrier concentration, which is given by Ni, which is equal to 10 power 10 per centimeter cube. This is the intrinsic carrier concentration in our semiconductor silicon bar. And again that 100% ionization of boron is given, so we know that we don't have any losses, so we have to consider our complete Na value. So now what we have to find is, we have to find the product of steady state electron and whole electron due to this light exposure. So we have to find out nothing else but the final steady state value of N and P, that is electron concentration at steady state and hole concentration at steady state, N and P respectively. So let us start with whatever data we have and whatever understanding of question we now we have. So let us move to next slide. So now, as we have already discussed, that boron is an acceptor type doping, that is we get Na after the doping. So now what is the value at equilibrium, that is before exposing these things to light. So as you know, in an p-type semiconductor, what we will have is majority carriers as whole. So now the complete doping which we are going to do will be reflected as P naught. So here the same thing we have used. Now based on your mass action law, what we will be doing is, what it is first, N into P is equal to Ni square. So now we have P naught and N naught at equilibrium initially. So now we will be rearranging this formula is this format, and then we will be solving. We will get N naught as 10 power 4 per centimeter cube. How? So as we know, the value of Ni is 10 power 10, that is whole square, which becomes 10 power 20 divided by a value of P naught is 10 power 16, which is given in the question. So it will be 10 power 16, which results to 10 power 4 per centimeter cube number of atoms in your bar, that is a p type bar. And this, what is the value of, what is 10 power 4? That is the number of electrons, that is minority charge carriers we have. So now let us move ahead. Now once we illuminate, that is illuminate means we expose our surface with light, what happen is some additional electron hole pairs are generated. Some additional electron hole pairs are getting generated. What is these pairs are? These pairs are electron hole pairs generated due to exposure of light or whatever energy we are acquiring. What we have taught about in the generation rate, those electron pairs will be extra due to illumination or exposure to light, and we already have our N and P values with us, older values, that is N naught and P naught, the earlier concentration at equilibrium before exposure to light. So what will happen is whatever whole electron pairs are getting generated will be added to the earlier value and we get the final value. So let us see how this number of holes and electron pairs generated will come into picture and what will be the amount. So now we can say delta P and delta N are the, see, whenever a whole electron pair is getting generated, the amount with which these pairs are getting generated will be equal. So delta P will be equal to delta N and will be given by G into tau. So what is G into tau? G into tau is your generation rate and lifetime. Means once the carrier is, how many carriers are getting generated and for how much time these carriers are remaining there in the semiconductor. So we already have the value of G, which is given in the question, provided to us in the question as 10 power 20 per centimeter cube second multiplied by, what is the value of tau? It is given as 100 microsecond, but we have already reduced it to 100 into 10 power minus 6 seconds. So that when we will solve it, we will get 10 power minus 4 seconds. So see, second will get cancelled and finally we will get our answer as 10 power 16 per centimeter cube. That is the value of holes and electron pairs getting generated. Okay. So now what is the new value of hole concentration or electron concentration? So that will be the addition of the equilibrium level hole concentration, that is your P naught, and the new holes are generated, that is your delta P. So this is the formula, P naught plus delta P, which will be, what is the value of P naught we have? We already have is 10 power 16 plus what is the value of delta P we have received, that is 10 power 16 again, which will be equal to 2 into 10 power 16. So this is the final value of, or a new value at steady state hole and hole concentration. So now let us solve in the similar way the electron concentration. So what is the value at equilibrium? That is 10 power 4, which we have deduced using mass action law, plus what is the value of newly generated electrons? That this is 10 power 16, as we have got it from this portion, and we are, now we can say approximately the number of 10 power 16 is very high as compared to 10 power 4. So we can say that we can neglect the equilibrium concentration of electrons, that is minority charge carriers, and we will consider whatever the amount of charge carriers getting generated presently. So that will be again 10 power 16. So what is the unit here? Per centimeter cube, per centimeter cube. So these are the two things which we will be getting. That is the value of a hole concentration and the value of electron concentration at steady state. Now what we have to find is not these things. We have to find the product of hole and electron concentration at steady state. So let us find that value again. So this is the final formula. That product will be n into p. What's the value of n? 10 power 16, as we have already seen on the last slide. What is the value of p? 2 into 10 power 16, as we have again deduced from the last slide. And finally the value becomes 2 into 10 power 32 per centimeter cube. These are the number of atoms of holes and electrons, that is count of holes and electrons in a volume having dimensions 1 centimeter by 1 centimeter by 1 centimeter. So as we can check from the option D is the correct solution. Once you take this, you will get 1 mark. Thank you. We will meet in the next session.